Jacques Charles was a French mathematician and physicist who lived from 1746 to 1823. He's credited with the invention of Charles' law, although he didn't actually publish it. Some guy, Gay-Lussac, did later, but Gay-Lussac credits Jacques Charles. So anyways, Charles discovered his law through his work with hot air balloons. So after the Montgolfier brothers made the first hot air balloon, Charles quickly followed suit, but he filled his with hydrogen gas, which is interesting because he basically knew that someone else had discovered that hydrogen gas is a thing and it's lighter than normal gas like air. And then Charles was also aware about how buoyancy works, and therefore his hydrogen balloon was more effective. It rose to higher heights than the Montgolfier brothers' balloon. And Charles filled his balloon through a reaction where he poured H2SO4, which is like an acid, into barrels of iron nails, and then this was like a substitution reaction, and so that iron would swap with the hydrogen and the hydrogen would rise out. And it's kind of a miracle that he didn't blow everything up because this reaction is really exothermic. But anyways, while he was working with hot air balloons, Charles observed that as he cooled the balloons, they would kind of contract, the gas in them, and as he heated them up, they would expand. And that basically explains how hot air balloons work, right? Because if you're heating it up and it's expanding, there's, less matter in more volume. So via buoyancy, it'll rise up. So this is Charles's law. Volume is proportional to temperature at constant pressure and amount. And like we saw with Boyle's law, we can take this kind of abstract relationship and make it into a workable equation. So initial volume over initial temperature should equal final volume over final temperature. This is intuitive, the ratio of volume to temperature should be constant if they are proportional. Okay, let's try a practice problem. So at a carnival in the afternoon, a child fills a balloon with 1.8 liters of helium at 25 degrees Celsius. They take the balloon home, and now it is evening, and the temperature has cooled to 20 degrees Celsius. Assuming no helium escapes the balloon, what is the volume of the balloon now? Okay, so one thing that's important to note when working with the gas laws, again, so we need to convert from Celsius to Kelvin. And why is this important? So Kelvin is a system that works with an absolute zero, and it'll quantify the amount of energy in the system because temperature corresponds to molecules bouncing around. But Celsius, it doesn't work with an absolute zero. Because something is freezing, it doesn't mean that it doesn't have any energy at all. And that's not the case for Kelvin. So we just always need to remember to convert things to Kelvin. And this relationship is Kelvin equals degrees Celsius plus 273.15. And you may or may not use this 0.15 part, just depending on sig figs and stuff like that and what an exam expects you to do, but yeah. Okay, so let's recall that our equation is initial volume over initial temperature equal to final volume over final temperature. So what do we know? Well, we know our initial volume, so 1.8 liters, and then we also know our initial temperature, but we will need to convert it. So this should be over 25 plus 273.15 Kelvin. And then we also know our final temperature. So what we're solving for is volume, of course. So V2 over 20 plus 273.15. Okay, so now we can just take out a calculator. If we multiply both sides by this denominator, we should get that V2 is equal to, time for some calculations. Yeah, remember to be efficient with your calculator on the pt.1 exam. I'm not right now, but it is important. Oh no, sorry this is taking so long. I'm not being super efficient right now. Okay, so this is going to be equal to approximately 1.7698. And then just remember to round to sig figs. So we'll only have two sig figs here because 1.8, that's like two places. So you'll just say that your V2 is equal to 1.8. So I guess this example doesn't work super well in a sig fig situation, but you can see that the volume does in fact change. So yeah, that's Charles's law, and I'll see you in the next video.